morning students. In today's class we are going to discuss about the field effect transistor FET and silicon controlled rectifier SCR. So in today's video we are going to discuss on the FET introduction, JFET construction and operation, JFET transfer and drain characteristics, and finally the square law expression for the drain current ID and the resistance Rin. So let us analyze what is the basic comparison between the bipolar junction transistor and field effect transistor. So bipolar junction transistor, as we have studied, it is a bipolar device. Bipolar device in the sense the current conduction is due to the charge carriers, electrons and holes. Whereas in the case of field effect transistor, it is a unipolar device, and the current conduction is due to one type of charge carriers, that is either electrons or holes. And BJT is a current control device, whereas FET is a voltage controlled device. And BJT possesses low input resistance, whereas FET it is having high input resistance. And the temperature coefficient is positive for BJT, and for the FET it is negative temperature coefficient. Transfer characteristics of BJT is linear, whereas for the FET it is non-linear. And as we have seen, the gain bandwidth product is greater for BJT, and for the FET it is small. And the main application of BJT is it can be used as an amplifier, whereas in the case of FET it is used as an ideal switch. So let us start with the field effect transistor. What is a FET? It is a voltage operated device and can be used in amplifiers and circuits. There are two different classifications of FET as JFET, that is junction field effect transistor, and the other one is MOSFET, metal oxide semiconductor field effect transistor. Under junction field effect transistor, again it is classified as two types, NJFET and PJFET. Whereas for the MOSFET, it is classified as two types, enhancement mode and depletion mode. Under enhancement mode, we have both P-type and N-type. Under depletion mode, again it is classified as P-type and N-type. So what is a JFET? It is a type of FET that operates with reverse bias PN junction to control current in a channel. So depending on the structure, we can classify the JFET as two categories, N channel or P channel. So the basic representation of a JFET is shown here, where you will be having a N-type semiconductor material and will be taking a 2 P-type semiconductor. It will be diffused inside the N channel to form the PN junction. So the three terminals of the FET are drain, gate and source. So for the gate, both the N-type material are combined to get a gate terminal, whereas the above terminal is the drain and the below one it is the source. Whereas for the P channel, we'll be having a P-type semiconductor where two N-type semiconductor are diffused inside the P-type material and they are connected together to form the gate terminal. And above the P channel it is the drain terminal and below it is the source terminal. So basically if you see a FET, it will have three types of terminals, drain, gate and source. So this is what we have seen now. So here we are going to explain about the JFET operation. And as we have seen now, the JFET consists of three terminals, gate, drain and the source. The gate and the source, it is always provided with a reverse bias with the help of an external DC voltage VGG. So VGG sets the reverse bias voltage between the gate and the source. And as I have told, it is always operated with gate source PN junction reverse biased. And we have another external DC voltage VDD which supplies the voltage across the drain and the source. This, this provides drain current which moves from drain terminal to the source terminal. So reverse biasing of this gate source junction with a negative gate voltage, definitely it produces a depletion region across the PN junction, and this depletion region will extend into the N channel, and thereby it decreases the resistance by restricting the channel width. So what happens here is the channel width gets controlled, and as well as the resistance offered by the channel will be more, and this can be controlled with the help of a gate voltage. So if the gate voltage is increased or decreased, thereby we can control the amount of drain current that flows from the drain to the source. So this is the basic operation of the JFET, and here we have shown the symbols of JFET, N channel and P channel. So how to differentiate this is the arrowhead which is inside the transistor terminal, it is the N channel. If the arrowhead it is going out of the gate terminal, then it is termed as a P channel, and basically it is having three gate terminals, drain, gate and source, and for the N channel the arrowhead will be flowing inside the transistor, inside the FET, whereas for the P channel the arrowhead will be flowing away from the gate terminal. So next it is JFET drain characteristics and parameters. So in order to draw the drain characteristics, we are going to have a graph between the VDS, that is the drain source voltage applied, and the drain current. So in the x-axis we are going to have the voltage applied across the drain and the source, which is termed as VDS, and the current which is flowing from drain to the source, which is the drain current, which is drawn across the y-axis. So as soon as the VDS voltage is varied starting from 0, we can observe there is a linear increase in the drain current ID. So if I keep on increasing the VDS voltage, the drain current increases and it reaches a maximum value of IDSS. So later this point is marked as point B on the graph, and the point at which the drain current reaches the maximum value, will call it as VP, that is the pinch off voltage, the voltage at which the drain current becomes maximum and further it will not increase. So this voltage will call it as pinch off voltage, which is marked as point B on the graph. So above the pinch off voltage, if I keep on increasing the VDS voltage, it seems to be saturation. The FET becomes saturation, and the current seems to be constant. And above the voltage, that is, for example, if VDS is equal to 25 volt, above, if I am going to increase the voltage, what happens to the current is it rises more rapidly, which is represented by the point C. Above C, we can observe the current increases rapidly, and this region we can name it as a breakdown region. And overall, if you see the characteristics, it is divided into 4 regions. One is the ohmic region, which falls between O, A, B, that is the as soon as the voltage is increased, the current increases linearly. So this region will call it as ohmic region, and in this region the JFET acts as a simple transistor, that is, if voltage increases, current also increases linearly. Whereas the next region is called as the saturation region or active region, where the current will be constant, even though if I increase the voltage from VP to VDS, say less than 25 volt. So this region where the current is constant for various values of VDS, we call it as saturation region. And above VDS, say 25 volt, the current increases rapidly. This region will name it as breakdown region. So this is about the drain characteristics of JFET. So as I told, the pinch of voltage at which the current reaches the maximum, and it will be a fixed value. So above that, if I increase the VDS value also, there will not be any change in the drain current, and the drain current is almost constant in this particular voltage. So this value of drain current, will call it as IDSS, drain to source current with gate shorted. It is represented as IDSS, that is the maximum saturation current. It is represented by IDSS. And as I told, there is a breakdown region above which which is marked as point C in the characteristics, above which if I increase the VDS voltage, the drain current increases very rapidly. So further increase may cause damage to the device.